So he has received his PhD from University of Antwerp Vision Lab, Belgium in 2012. Currently, he is working as an assistant professor in the Department of Computer Science and Engineering in ITK Surathkal. He has published more than 70 articles in leading journals and conferences, and his research interests include image processing, deep learning, and medical image analysis. So, with this short biodata of Dr. Rajan, over to Jeny Rajan.
So good morning, one and all. In this lecture, I will present some of the basic concepts related to artificial neural network. So we will discuss some of the very basic concepts. That mean we will see how an artificial neuron learns and how to build a neural network. By neural network, I mean the traditional neural network. This is not the convolutional neural network, but an understanding of artificial neural network will really help you in understanding how a convolutional neural network learn. So we will also discuss the limitations of artificial neural network in processing images. So we know that artificial neural network, especially convolutional neural networks, are the state of the art or among the most powerful machine learning techniques, right? So convolutional neural networks are currently used in image processing, computer vision, natural language processing, and so on. If you have a large amount of data, then of course, and if you want to do a supervised learning, then of course your choice will be always convolutional neural network, because convolutional neural network has some advantage over the traditional machine learning algorithm. So artificial neural networks are basically inspired by the working of brain. So motivated by the working of biological neuron, McCulloch and Pitts created the first artificial neuron. So we will come to those papers in the coming slides. And the universal approximation theorem states that with enough neurons and with enough hidden layers, you can approximate any function with the help of artificial neural network. That shows the power of artificial neural network. So the history of artificial neural network began with the paper published by Warren McCulloch and Walter Pitts in 1943, who created a mathematical model to simulate the working of a biological neuron. So this slide here, you can see a brief history of neural network. And in this presentation, I will try to discuss some of these basic or groundbreaking papers. So artificial neural networks are basically inspired by the biological neuron. So you know that our central nervous system is built up of nerve cells or neurons. So here you can see the anatomy of a neuron. So these are the important components: the dendrites, cell body, axons, axon terminal, and all. A neuron receives the input through dendrites. Right, the dendrites collect the data from other cells or from other cells in the sensory organs, and it will be processed. And based on the strength of the input data, the neuron may fire or it may not fire. So, and this information will travel to the next neuron through the axon. So here there is axon terminal, and at the junction there is something called synapse. So through this synapse, the neuron communicate to the other neuron. So usually there will be millions of connections, right? So a neuron can take input from a large number of other neurons. So this is how a biological neural network work. So inspired by the working of biological neuron, so Warren McCulloch and Walter Pitts designed a mathematical model of it. So we cannot compare the model developed by McCulloch and Pitts with the biological neuron, because biological neuron is very complex, but the model that they developed is a very simple model that emulates a biological neural network. Biological neuron. So their work was published in 1943 in the Bulletin of Mathematical Biophysics, and this is the title of their paper: A Logical Calculus to the Ideas Immanent in Nervous Activity. So this is the first paper that introduced artificial neuron, and this paper is again considered as a classical paper in artificial intelligence and neural network. So we will see what is their contribution in this paper. So this is the first mathematical model that describes an artificial neuron. So here you can see two images. The first one is the biological neuron, and here you can see an artificial neuron. So we'll look at the similarity. So you can see that in the case of a biological neuron, it takes the input through the dendrites, and the equivalent of dendrites in the artificial neuron is these inputs. So we have, it can take n inputs, and there is a weight associated with these inputs. This weight corresponds to the synaptic strength in biological neuron. So, and in the nucleus, we will do a linear combination of the input and weight. We will compute the weighted sum. And if the weighted sum is greater than a threshold, the neuron will fire. Otherwise, the neuron will not fire. So this is the model that they developed. So you can see that first here we will compute the weighted sum. If there are n inputs, there will be n weights associated with the inputs. So we will compute a weighted sum. This weighted sum will be given to an activation function. So this activation function, here we have a step activation function. So if the weighted sum is greater than a threshold, then the output will be 1. Otherwise, the output will be 0. So this model is very, very simple. So mathematically, you can describe all these things like this. We are computing the weighted sum, and the output is equal to 0 if sum less than the threshold, and output is equal to 1 if the sum greater than threshold. So this is the model that they designed. This is a very simple mathematical model that emulates a biological neuron. So even though the model is very simple, you can use this model to design you can use this model to do simple arithmetic and logical operation. You can even create logic gates using this model. So here we will see how to design a logic gate using the model developed by McCulloch and Pitts. So I assume you all know how these logic gates work. So here we have the ground truth of the AND gate. So the AND gate, you will get an output 1 when both inputs are 1, right? Otherwise, in all other cases, all other combinations, the output will be 0. So now what we are going to do is we are going to create the AND gate using the MB neuron. So this is the neuron that we are. This is how my neuron look like. So it takes 2 inputs. A and B are the inputs, and WA and WB are the weights associated with the inputs, and Y is the output. So when A and B are 1, this neuron should fire. In all other cases, the output should be 0. Otherwise, the neuron should not fire. Right. So what value of WA, WB, and T helps in achieving this output? This is what we have to calculate, right? So the parameters in this model are WA, WB, and WA, WB, and T. So we have to come up with the optimal values of this parameter to make this neuron act like an AND gate. Right. So we know that this neuron should fire only if A and B are 1. In all other cases, the output should be 0. Right. So when A is equal to 0 and B is equal to 0, the model should not fire. That means the weighted sum should be less than T. So if the weighted sum is less than T, then the model will not fire. Right. So when A is equal to 0 and B is equal to 0, that means the weighted sum should be less than 0. That means 0 into WA plus 0 into WB, this value should be less than or equal to T. Or T should be greater than 0. So when A is equal to 1 and B is equal to 0, in this case also the neuron should not fire. So if you look at this equation, then we will get WA should be less than T, because 1 into WA is WA plus 0. That means WA should be less than T. And when A is equal to 0 and B is equal to 1, in this case also the neuron should not fire. So WB should be less than T. When both A and B are 1, the neuron should fire. That means WA plus WB should be greater than T. Now we have a system of equations here, and we have to come up with the appropriate values of WA, W, and T to satisfy this equation, right? So of course, there exist many solutions. So here I substituted the value of A and B as WA and W and B as 1 and T as 1.5. So these values satisfies this equation, and you can see that when WA is equal to 1 and WB is equal to 1 and when T is equal to 1.5, this neuron will act like an AND gate. Right. So of course you can give, there are other values that also satisfies this equation, because there exist multiple solutions to this system of equations. So this is how we can design a logic gates using a McCulloch and Pitts model. Of course, you can see that this model is very simple, but even though the model is simple, you can design logic gate. If you can design logic gate, that means you can design more complex circuits. So that was the idea. The idea was to design a computer using these neurons, artificial neurons. So, however, one drawback of this model is that, if you want to find the optimal values of these parameters, then you have to solve a system of equations. We have to solve these equations manually, right? So, in this case, the number of parameters are less. We have only 3 parameters here. So, when the number of input increases, or when the number of parameters increases, then it becomes difficult to find the to solve these equations. So, to come up with the optimal values of these parameters. So, this is one drawback of McCulloch and Pitts model. The other drawback is this model will work only if the input data is linearly separable. So if the input is not linearly separable, then this model will not converge, or you will not be able to come up with an optimal solution. So you can see that so you can design and or not gate using a MB model, but you will not be able to design an XOR using one single MB model. Because you can see that in the case of XOR, the input is not linearly separable. So in the case of AND, you can see that the output is 1 when A and B are 1. In all other cases, the output will be 0. So you can easily separate these two outputs with the help of a line, right? In the case of an OR, so you will get a 1 if at least one of the input is 1, otherwise it will be 0. So you can easily separate it with a line. But in the case of XOR, that is not the case. So output will be 1 when at least one of the input is 1, other will be 0, right? So the input is not linearly separable. So you will not be able to solve this problem using McCulloch and Pitts model. So these are the drawbacks of MV model. The model is simple, and they come up with an artificial neuron. And you can use this model to solve some of the mathematical and logical operations. However, the drawback is the model will work only if the data is linearly separable, and then you have to solve a system of equations manually to find the optimal values of the parameters. So this is a drawback of this model. And to address some of the drawbacks of MB model, Rosenblatt come up with an improved model that was published in 1958, and his model is called Perceptron. So he designed a model, and based on that model, he designed a device called Perceptron. This device was able to recognize the basic shapes like a triangle, circle, and all. So we will see how this Perceptron work. So Perceptron is very similar to MB model. The only difference between Perceptron and MB model is that in Perceptron, Frank Rosenblatt introduced a learning rule. So this model is automatic when compared to MB model. MB model is not automatic because you have to manually find the optimal value of the parameters. Here, the value of the parameters can be automatically identified with the help of a learning rule. So he introduced a learning rule, or he used a learning rule to train the perceptron or to find the optimal values of the parameters. So the other modification that he did is he made some small change in this equation. So if you look at the MB model, this is how the model works, right? You have to compute the weighted sum, and if the weighted sum is greater than the threshold, the neuron fire. Otherwise, the neuron will not fire. So he moved this this threshold to the left side of the inequality. This is just a notational change for simplifying the calculation. And he used the terminology bias. This bias is nothing but minus t. And bias is a measure of how easy it is to get the perceptron to output 1. So this is just a notational change to make the calculation, to simplify the calculations. So this is one modification that he did. And the other contribution is he introduced a learning rule. So now we will see how this perceptron learned. So this is how the perceptron learning rule look like. So assume this is our model. So you can initialize these weights randomly. So after initializing these weights randomly, then you have to iterate through the algorithm to find out the optimal value. So assume we initialize these values randomly, then the W's or the parameters are updated like this. I plus 1 is equal to Wi plus delta W. Wi plus 1 is a new value, and Wi is the current value. So we are updating the current value using this formula. Wi plus 1 is equal to Wi plus delta W, and delta W is computed like this: eta into R into X, where X is your input and eta is a learning parameter. Usually the value of eta is between 0 and 1, and R is the difference between the predicted output and the expected output. You just assume that y is the expected output and a t is the predicted output. So if there is an error, that means the value of the parameters are not optimal and you have to update it, right? So if error is 0, you can see that delta W will be 0 and weights will not be updated. Otherwise, the weight will be updated. Similarly, the bias also will be updated. So this is how the weights in Perceptron gets updated. So he used a learning rule, and this learning rule is basically borrowed from this particular book, Organization of Behavior, written by Hebb. So he used this the learning rule introduced by Hebb in the MV model as to automate the working of a MV model. So this is how the Perceptron learns. Perceptron is automatic. So this neuron is automatic. This neuron learns automatically with the help of the perceptron learning rule. So the weights can be initialized randomly. So we will initialize the weight and the bias randomly. Then we will use this iterative algorithm to update the value, and this process will continue till the error become less than a tolerance level or error becomes 0. Right. This is how the perceptron learning rule work. So one advantage of Perceptron when compared to MB model is that MB model is not automatic, but Perceptron is automatic. You don't need to solve a system of equations to find the optimal values of the parameter. So that will be identified automatically. But again, the other drawback is still there. The Perceptron converges only if your data is linearly separable. So if your data is not linearly separable, then you will not get optimal values with the perceptron. So this is one drawback of perceptron. The other drawback of perceptron is see, perceptron is not a large margin classifier. That means if you look at the decision boundary of if you look at the decision boundary generated by perceptron, you can see that the margin is very less. So this is an experiment with the perceptron in classifying two flavids. So you can see that if you look at this image, you can see that the data is linearly separable. You can separate these two classes with a line, but this is the boundary generated by perceptron. So you can see that this boundary is not optimal. It is possible to draw a better boundary, better decision boundary like this. So if the data is linearly separable, then you don't need to bother about it, but assume that the data is not linearly separable. So in that case, if your classifier is not a large margin classifier, then the error generated by that classifier will be more. So this is one drawback of perceptron. Perceptron is not a large margin decision boundary, a large margin classifier. So this is mainly because of the perceptron rule itself. You can see that here we are using a step function. So this drawback is mainly because of the step function. So we will be getting, first we are computing a weighted sum, then we are thresholding it to either 0 or 1. So there itself we are introducing this error, right? So whatever, see, assume the threshold is 5 and we are getting an output 10. And in another case, assume we are getting an output 15. So the model will not differentiate between these two output. Whatever be the output, if it is greater than t, it will assign to one class. Otherwise, it will assign to other class. So this is the reason why the margin is not large. So this is one drawback of perceptron. The other drawback is it will not it will work only if the data is linearly separable. So to address the drawback of perceptron, or to improve the performance of perceptron, in 1960, Bernard Widrow and Ted Hoffer come up with Adaline. So Adaline is again a very powerful model. So Adaline is the base model that is used in most of the modern CNNs or ANN is Adaline. So Adaline is an algorithm and that made a huge impact. So the difference between Adaline and perceptron is that in perceptron, the difference is in the learning rule. In perceptron, they used the perceptron learning rule, and in Adaline, Bernard and the authors used the gradient descent algorithm to train the neuron. So we will see how the gradient descent algorithm work, and we will try to come up with a learning rule based on the gradient descent method. So you just assume that, so in this screen you can see some graphs. So you just assume that you are standing somewhere here and we have to move from this particular position to this particular position. And we have to move through this line. So this is our initial position and we have to move from here to this particular point, right? How will we move? So you can move against the slope, right? So you can see that this line has a positive slope, and you have to move against the slope to reach here. And when you move, you can take a small step or you can take a large step, right? So if you take a small step, then it will take much time for you to reach here. And if you're taking a large step, you may overshoot the minima, overshoot this particular point. So this is again a hyperparameter. So to move from here to here, you can use this equation, x is equal to x minus alpha into m, where m is the slope. X is your current position. So you have to update. We are standing here. We will compute the slope, and then we can take the next step. So we will reach here. You can take the next step. You will reach here, and so on. Finally, we will reach here. Right. So this step size is alpha. We call it as the learning rate. Right. So this is how we move from this point to this point to this point through this line. So since it is a line, the slope is same everywhere. Right. Now you just assume that we are moving through this line. So difference between these two lines is, in this case the slope is positive, and in this case the slope is negative. But again, you can use the same equation. So in this case we have to move along the slope. Here you have to move against the slope, right? But you can use the same equation. In this case, the slope become negative, so the equation will become x is equal to x plus alpha into m. So this may be our initial position. You can take some small step size, you will reach here, and you can continue moving, and finally we will reach here. Now assume that you are traveling through this particular curve. We have some sinusoidal curve here, and assume that we are traveling through this curve. We are standing here. So how will we move? So the difference between this shape and this shape is that here we have a line, and the slope is same everywhere. For all the pixels, the slope is same, right? So here the slope will be different, right? So how will you compute the slope of a curve? You have to take the derivative, right? So you have to compute dy by dx, and dy by dx will be different at a different locations, right? So again, we can use the same equation. So we assume that we are standing somewhere here. So you can compute the derivative, and if the derivative is um, if it is positive, then you have to move in this direction, and we will continue moving in this direction. And when we reach here, we will stop. Right. So at this position, the derivative will be 0. So this will not, the x will not update, right? X is equal to x minus 0, so x will not update. So we will reach here. So if you are here, then you have to move along the slope, right? So when you reach here, you will stop, right? So this is how we move through this particular curve. Now assume that you're in this case our y depends only on one parameter x. Now assume that y is a function of multiple variables. So assume that y is a function of x1 and x2. So in this case, we have to find what value of x1 and x2 minimizes the y. So here we have to find what value of x minimizes the y, right? So here you have to find what value of x1 and what value of x2 minimizes the y. So we have to take the partial derivative. So we have to update both x1 and x2. So how will we update x1? So x1 will be x1 minus, you can use the same formula. So new value of x1 will be x1 is equal to x1 minus alpha into dou y by dou x1. We have to take the partial derivative because here we have two variables, right? And in the case of x2, the new value, we will update x2 like x2 as x2 is equal to x2 minus alpha into dou y by dou x2. So these derivatives you can put as a vector, and you can call this as a gradient. So this gradient is a collection of partial derivatives, right? So we call this as a gradient, and we have to find what value of gradient minimizes this y. This is what we do with the gradient descent algorithm. So when the surface is something like this, a convex surface, it will not be that difficult to reach here. So maybe we will be initially here or here. In the end, we will reach here because this is a convex surface. But if you are traveling through a surface like this, where there exist many local minimas, there is always a chance that we can fall into some of these local minimas. So because the derivative is 0 here, derivative is 0 here. So if you fall in some of these local minimas, sometimes we will not escape from those minimas, and as a result we will get a suboptimal solution. So we should be very careful, but there exist some algorithms that help us to escape from local minimas, right? So this is how the gradient descent method work. And Widrow and Hoff used the gradient descent algorithm to update the the weights. So in the case of Perceptron, they used the Perceptron learning rule. We saw what is a limitation of Perceptron learning rule. So with Perceptron learning rule, you can train a neuron, but the classifier is not a large margin classifier, right? So now we will see how can we use the gradient descent method to train a neuron. So this is the neuron that we are going to consider. So this is again a simple neuron. It takes two input, x1 and x2 are the inputs, and w1 and w2 are the weights associated with x1 and x2. So first we have to compute the weighted sum. That will be x1 w1 plus x2 w2 plus b, where b is the bias of the neuron. So first we have to compute the weighted sum, and this weighted sum we will give it to the activation function, right? So the activation function that we are going to use here is an identity function, again a linear activation function. So since the activation function is an identity function, y will be equal to a. And the other thing that we have to consider is how we are going to compare the output. Y is the output of the model. This is the predicted output. So we have to compare the predicted output with the actual output, right? Assume T is the actual output. They used the mean squared, the squared error to compare the output. So this is how the error is computed, or this is the loss function that they used. E is equal to half of T minus Y the whole square. This half is to simplify the calculation that we will see. So we should be careful with the loss function and the activation function, because if you want to use gradient descent algorithm, make sure that the loss function and the activation function that you use is differentiable. So this is the loss function that they used, and the activation function used was an identity function. So y is equal to a. So now we will try to derive a weight updation formula for this particular neuron using the gradient descent method. So I have to find what value of w1. So what are the parameters in this model? The parameters in this model are w1, w2, and b. So we have to come up with the optimal values of values for these parameters to get an output that is very close to the target output, right? So I want to update. So you can initialize. So when we start, we will initialize with the random values, and then we have to update w1, w2, and b, right? So you have to derive a weight updation formula. So here I am going to derive a weight updation formula. So w1 is equal to w1 minus alpha into dou e by dou w1. This is again same as what we seen here. So our initial w1 will be somewhere here. You just assume that when we randomly initialize, it will be somewhere in that curve, and then we have to update w to reach the global minima. So since we are using gradient descent method, this is how we are going to update the w, right? So the new value of w1 will be the old value minus alpha into dou e by dou w1. So this equation came from here. This we already discussed. Now we will try to solve this equation. So w1 is equal to w1 minus alpha into dou e by dou w1. So what is dou e by dou w1? So you can see that e is again a function of y. So we can apply the derivative chain rule. So dou e by dou w1 become dou e by dou y into dou y by dou w1. So since y is again a function of a, so you can apply derivative chain rule again here. So dou y by dou w1 become dou a by dou y by dou a into dou a by dou w1. So dou e by dou w1 will be dou e by dou y into dou y by dou a into dou a by dou w1. Now we will solve these terms separately. So what is dou e by dou y? So we know that e is equal to half of t minus y the whole square. If you take the derivative with respect to y, we will get minus of t minus y. This half and this will cancel each other. That is why they used a half here. And dou y by dou a will be 1 because y is equal to a. And dou a by dou w1 is, see, this is our a, the weighted sum. And we are taking the derivative with respect to w1. So the output will be x1. So dou e by dou w1 will be minus of t minus y into x1. So if you substitute this one, this value in this equation, we will get the weight updation formula. So this is how we are going to update w1, right? New value of w1 will be old value plus alpha into t minus y into x1. So we derived a weight updation formula for w1. Similarly, you can derive the weight updation formula for other parameters like w2 and b. Right. So this weight updation formula is also called the Woodrow-Hoff learning rule, and this learning rule is based on the gradient descent algorithm. So we will see what is the advantage of using the Woodrow-Hoff learning rule instead of Perceptron. So since we are using this gradient descent algorithm, this classifier will be a large margin classifier. So this has an advantage with, when compared to perceptron. But however, if you want to use the gradient descent algorithm, as I told earlier, make sure that our error loss function and activation functions are differentiable. Otherwise, you will not be able to solve these equations, right? So we will see the difference. So this is how the perceptron work, and this is how the Adaline works. So we will compute the weighted sum, and this value we will give to the activation function. So that activation function, whatever be the output, if it is greater than t, output will be 1, otherwise a 0, right? And then if the output, if there is an error, then the weight will be again updated, and this process will continue till we will get an acceptable error rate, right? And in the case of Adaline, there's a small change. So you'll compute the weighted sum, and the activation function that they used is a linear activation function, or they used an identity function. And this output will be compared with the so the output of this model will be compared with the expected output, and if there is an error, this will go back. This is how it will train, and in the end, we will quantify the output. Right? This is the difference. And because of this, since we are not thresholding the output here, this the Adaline the margin of the Adaline will be better when compared to perceptron. But however, since we are using a linear activation function, so here we used an identity function, right? Since we used a linear activation function, this model also work only if the data is linearly separable. So if the data is not linearly separable, then this model will not work. Even if you create a neural network with this linear neuron, still the output will be linear, because a combination of linear function will be again a linear function. So it doesn't matter how many linear neurons you use to create a neural network, the output will be again linear. But in practice, see, the data will not be linear separable, right? So if the data is not linearly separable, then these models will not be useful. So we have to create a neuron that is we have to create a neuron with a non-linear activation function. So here we used a linear activation function. So instead of using a linear activation function, we can use non-linear activation functions in the neuron to create non-linear models, right? A neural network that is that can that can come up with a boundary for data that is not linearly separable. So you can use different non-linear activation functions, but some of the popular activation functions in the literature are Sigmoid, TANH, ReLU and all. So we'll discuss some of these activation functions, and we will see how can we incorporate these activation functions in the neuron. So Sigmoid is again one of the most popular activation functions. So this is so it has an S-shaped. So this is the shape of the sigmoid activation function. And one advantage of sigmoid is it is bounded. The value is between 0 and 1, right? This is the definition of sigmoid. So y is equal to 1 divided by 1 plus e raised to minus x. So x is the input and y is the output, right? So when x tends to infinity, y tends to 0. And when x tends to infinity, y tends to 1. And when x tends to minus infinity, y tends to 0. So the output is always between 0 and 1. And sigmoid is a differentiable function. So there is the derivative of sigmoid exists. So this is a derivative of sigmoid. So if y is the output, the derivative will be y into 1 minus y. So we can use sigmoid in the Adaline, and we will see how it works. So one advantage of sigmoid in using in this one is, see, in the previous case, when we used an identity function, you can see that the output is not bounded. When the output is not bounded, then it will be difficult for us to find an optimal threshold, right? So that was one drawback with this particular model, the one we discussed earlier. So this can be solved with the help of a function like a sigmoid. So sigmoid is bounded. You can see that the output is between 0 and 1. So you can set a threshold like 0.5 or 0.6, right? So now, and again, another advantage of sigmoid is this is a nonlinear function. So with a nonlinear activation function, you can create better classifiers, right? Even if your data is not linearly separable, or even if the distribution of your data is complex, by using a combination of many nonlinear neurons, you will be able to come up with a surface that can separate the data, right? So now what we are going to do here is we are going to come up with the weight updation formulas for a sigmoid neuron. The difference between this particular neuron and the neuron that we discussed earlier is the one we discussed earlier, that was having a linear activation function. So in this case, the activation function is non-linear. We used a sigmoid activation function. So the only difference is in the activation function. So we are using the same loss function, again the square difference here, and this activation function we change to a sigmoid activation function. So everything else is same. So again we are using the gradient descent method to update the weight, to derive the weight updation formula. So this is how we are going to update the parameters. W1 is equal to W1 minus alpha into dou E by dou W1. So all these things we discussed. So the only change is here. So dou y by dou a, it was 1 in the previous neuron because we used an identity function. So here this will be y into 1 minus y. This is nothing but the derivative of sigmoid. So when you substitute all these values, you will get a weight updation formula. So this is the weight updation formula for a sigmoid neuron. So we have one additional term here, y into 1 minus y. So for the identity for the other neuron that we discussed earlier, this term was not there because we used an identity function as an activation function, right? So this can also create problem that we will discuss in the coming slide. So now our neuron is a nonlinear neuron. By using a combination of nonlinear neurons, you can create a better classifier. But see, you should look at the derivative value of this sigmoid. So here you can see the derivative. If you look at the, yeah. So here you can see the derivative of a sigmoid. So this is a sigmoid function and this is a derivative of the sigmoid. You can see that the derivative of sigmoid is less, right? So when the derivative value is less, then this can slow the learning process. So your neuron will learn very slow when the derivative value is less. So sigmoid neurons are powerful. You can create a nonlinear classifier, but sigmoid neuron learn very slow because the derivative of sigmoid is less. Here you can see the classification surfaces generated by different models. So this is how Perceptron. This is a boundary generated by classification boundary generated by Perceptron. This is with Adalen. You can see that the data is not linearly separable. So with these models like a Perceptron or Adalen, you will not be able to classify these two data, right? So this is one class and this is another class. So since it is not linearly separable, that means you will not be able to separate these two with a line. Whatever way you draw the line, and see you will not be able to separate these two classes properly. So this is a decision boundary generated by Perceptron. The decision boundary generated by Adalen may be slightly better. Error will be less, but since in Adalen they used an identity function, and since it is a linear activation function, that is again a linear classifier. So if you use sigmoid, you can see this is the decision boundary generated by sigmoid because we used a non-linear activation function. So with the help of with the help of a more sigmoid neurons, or if you create a network of nonlinear neuron, you will be able to create come up with this boundary for more complex data distributions. But however, in this case, so if you look at this slide, you can see that the error function that we used is a mean squared error, and the activation function that we used is a sigmoid function. But the problem that we want to solve to do is a classification. The output will be 0 or 1. We have only two classes. So in that case, sigmoid is not a, MSE is not a preferred loss function, because when we use MSE, we assume that the underlying data is generated from a normal distribution, but that is not the case here. So we have to classify the data into two classes, right? So the data usually come from we can approximate it with the Bernoulli distribution, right? So instead of using an MSE as a loss function, so if you want to do a classification, it's better to use cross entropy. So since in this case we have only two classes, so you can use a binary cross entropy as a loss function. So this will work better if you want to do a classification. So see here we used MSE. So instead of MSE, you can use a binary cross entropy. So here I am trying to solve these equations with the binary cross entropy. So the activation function is again sigmoid. So I changed the loss function to binary cross entropy, and we did all these. Once after substituting all these values, so this is the update formula that we got. So if you look at this update weight updation formula, you can see that this derivative term is not here. That means if you use binary cross entropy, then your neuron will learn faster than using MSE. Right. So here we used MSE as a loss function. So here we used binary cross entropy as a loss function, but the activation function is sigmoid in both cases. So if you look at the weight updation formula, you can see that if you use this weight updation formula, then your neuron will learn much faster than the previous one. So you should be always careful in selecting the loss function and the activation function. If you simply choose some loss function and some activation function, that influence the performance of your model. So you should know what activation function I should use and what loss function I should use. So that selecting the appropriate loss function and the activation function, you can improve the performance of your model. Right. So see, if you look at the literature, you can see other popular activation functions like ReLU or TANH. So we will see how TANH and ReLU are different from sigmoid. So here you can see the definitions of a TANH and ReLU. So both TANH and ReLU are differentiable. That means you can use TANH and ReLU instead of sigmoid here. Since it is differentiable, of course you will be able to come up with a weight updation formula. So if you look at the TANH, you can see that TANH is also bounded. The value is between -1 and 1. So since this is centered around 0, but sigmoid is not centered around 0, but TANH is centered around 0. Since TANH is centered around 0, see when you update the weight, so this derivatives can move in both direction, both positive and negative direction, and as a result, your model may converge faster than a sigmoid neuron. So if you use a TANH, then since the derivative vector moves in both directions, your model will converge faster when compared to sigmoid. The other advantage of TANH is the derivative of TANH is higher when compared to, so here you can see the derivatives of different activation functions. So these are the 4 activation functions that I plotted here, and these are the derivative. So this is the derivative of a sigmoid, and this is the derivative of TANH. You can see that the derivative of TANH is higher than the derivative of sigmoid. So a TANH neuron will learn faster than a sigmoid neuron. So this is advantage of using a TANH neuron. So instead of using a sigmoid neuron, if you use TANH, then your neural network will learn much faster. But the output of a TANH is in the range -1 to 1. So this is the reason why people use a sigmoid in the outer layer. In the outer layer, if the value is between 0 and 1, then it is very easy for us to do a classification. But in the hidden layers, usually nobody use sigmoid. The reason is sigmoid neurons are very slow. It learns very slowly. Say if a sigmoid neuron is taking 6 hours to learn, then TANH neuron may learn the same thing in 3 hours, right? If you convert these hours to days, if a sigmoid neuron is taking 6 days to learn something, then with the TANH you can do the same thing with 2 days or 3 days, right? So this is the advantage of TANH over sigmoid. And if you look at ReLU, then see, this is the definition of ReLU. The output will be max of 0, x. If the input is x, the output will be max of 0, x. So you can see that in the right side, this is again a linear activation function. Left side, it will be 0, right? So if you look at the derivative of ReLU, you can see that if the value is greater than 0, then the derivative will be 1. So ReLU neuron learn much faster than TANH neuron or sigmoid neuron. So actually this ReLU is almost, this is an experiment, this experiment I took from some paper. So in that experiment, they used the CIFAR dataset and they demonstrated that ReLU neuron is almost 6 times faster when compared to sigmoid neuron, not sigmoid, TANH neuron. So then why we should use TANH in the hidden layer? So you will use ReLU, right? If you use ReLU, then your model will learn much faster than using sigmoid or a TANH neuron. So that is why I told when you design a neural network, you should be very careful with the different layers and the activation function and the loss function. So usually in the output layer, people use sigmoid activation function because the reason is sigmoid is bounded between 0 and 1, so it is easy for us to set a threshold. But in the hidden layer, you can use a TANH or ReLU. But of course, since the ReLU has some advantage over TANH and sigmoid, usually the developers or the researchers use TANH activation function in the hidden layers. But however, even though ReLU neurons or ReLU learns better than TANH neuron, one drawback of ReLU is that the ReLU is not bounded. So the output will be between 0 to infinity, but TANH is bounded. That is one advantage of a TANH over ReLU. So if you want to use, when we use ReLU in the hidden layer, usually you have to do some kind of normalization to scale your data again between some minus to positive range. But that you don't need to do if you use TANH neurons. So now we studied how to train a single neuron. But here you will see how to train a neural network. So see, with one neuron, see, we will not be able to solve the complex problem, right? We have to build a neural network. So when we build a neural network, how will we train the neuron? So here you can see I have a neural network with 3 neurons. So this is the input layer. We have one hidden layer and we have an output layer. In the output layer, so we know how to train this neuron. So here we know what is the expected output. So assume T is the expected output and Y is output of the model. So you can compare Y and T, and then accordingly you can update the parameters of this particular neuron. So W5, W6 and the bias of this one, right? But here we don't know what is the expected output. Then how can we update the parameters of these two neurons? This is again simple. You can again use the derivative chain rule. So you just assume that this is how our architecture look like. So we have an input, and this is a first hidden neuron. This is a second hidden neuron, and this is the output neuron. So in the output neuron, again, we know how to train this output neuron because we know here we can calculate the error. So W3, updating W3 is very easy. So the new value of W3 will be old value of W3 minus dou E by dou W3, right? But how will we update W1 and W2? So again, you can use the derivative chain rule. So see, once we give this, once we randomly initialize the parameters, and if you do a forward pass, in the end here we will get some error. So error means all these parameters are contributing to the error, right? So we want to come up, our objective is to come up with the optimal values for all these parameters. So what value of W1, what value of W2 and what value of W3 minimizes the error. This is what we have to find. So dou error by dou W1, that means what value of W1 minimizes the error. This is what we have to find. So dou error by dou W1 will be dou error by dou output into dou output by dou hidden 2 into dou hidden 2 by dou hidden 1 into dou hidden 1 by dou W1. So this is how you can compute dou error with respect to dou W1. Once you can compute this term, you can easily update W1. So new value of W1 will be W1 minus this value, right? So similarly, you can compute, you can update W2, W3 and so on, right? So this is called the back propagation. So here you can see how to update these 3 neurons. So updating the parameters of this particular neuron is straightforward. This we already discussed. So the parameters of this neuron are W5 and W6. So since you know the output, we can easily update these two parameters, W5, W6 and the bias of this neuron. So for this one, we have to update we have to use the derivative chain rule. The only difference is that when you have more number of layers, the number of terms will also increase. So if you look at this weight updation formula, you can see that the length is less. So when but if you come to the weight updation formula for W1 and W2, So here you can see there are more derivative terms involved, and as a result, your weight updation formula, the length of your weight updation formula will also increase. So if you are, in this case, we have only 2 layers. If you have 10 layers, then you can imagine how many terms will be there in this equation, right? So this is again easy. We have to do, we have to calculate the derivative, the partial derivatives, and then we have to again update the parameters, and again you have to do a forward pass. But in practice, you don't need to do these calculations, because almost all these deep learning frameworks, it has a built-in function to do backpropagation algorithm, right? Backpropagation. So you don't need to you don't need to write any algorithm to do it. So you can call the built-in function to do it. But this is how the backpropagation algorithm work. So this is how this process will work, the algorithm will work. So we have a model. Assume we created a neural network. You have to do you have to randomly initialize the parameters of the model. Then in the forward pass, we have to calculate the output of each and every neuron. Then in the end, we will get an output, right? So that output you have to compare with the expected output, and if there is an error, then you have to propagate back. So you have to calculate the derivatives. That means dou e by dou parameter. What are the parameters? You have to calculate the derivative with respect to all the parameters. Then we have to again we have to update the parameter. Then again you have to do the same process. We have to calculate the we have to compute the output again. So you can see that the error is coming down. So again, you have to continue this process. This is an iterative process, and you have to compute. You have to do this process till the error reaches an accepted level. But if the error is not coming down, that means your model is not learning. You have to change the model. So when you do this process, naturally, if your model is learning, then the error will come down. But if the error is not coming down, that means your model is underfitting. Your model may be too simple to learn the given data. In that case, you have to increase the complexity of the model. This we will discuss in the in another slide. So now we will see how can we use a traditional neural network to do image classification. So here we have a very simple model. So this is the data that we want to classify. So the input is handwritten digits, and I'm using a traditional neural network. So we created a simple neural network. So this neural network has only one layer where we have 10 neurons. So the output, the expected output is 10 classes, because the input digits are in the range 0 to 9. So if we give input 0, then this neuron should fire, and if we give 1, then this neuron should fire, and so on, right? So this is how my model look like. So I have 10 neurons, only one layer, and this is my input. So the input image size is 28 by 28. So I cannot give the image as such as input. So what I did is I converted this image to a column format. So there will be 784 pixels. So this is the input. So 784 pixels will be there. And this is again a fully connected network. So all those 784 pixels are connected to this one. It will be connected to this neural network, this neuron, and so on. Right. So if you look at this model, then you can see some limitations of the traditional neural network in processing images. The one drawback is see, we lose the spatial relationship between the pixels. So when we convert an image from convert a 2D image to 1D form, we will lose the spatial relationship between the pixels. So spatial relationship between the pixel is very important when you work with images. So this is one drawback of using the traditional neural network to do image processing. The other drawback is the number of parameters. See, if you look at this model, and if you look at this particular neuron, you can see that this neuron has 784 connections. 784 connection because the size of the image is 28 by 28, right? So 784 pixels means here we have 784 weights. So 784 W's and one parameter. So total number of parameters with respect to this particular neuron is 785. And the total number of parameters in this model is 785 into 10. So 7850 parameters are there in this model. So this is a very simple model, Still, it has 7,850 parameters, right? So you just assume that if we increase the size of these images, then see here it is a sound, here it is a 28 by 28. If it is a 100 by 100, then the parameters will increase by many fold. So the problem is the scalability. So you cannot simply scale an artificial neural network with just one layer. We saw how many parameters are there. So when the number of parameters increases, there are two issues. One is see, to train the model, you have to bring your model and the data to the memory, right? So if your model is taking too much memory, then it can be a problem. Sometimes the memory will not be able to hold the model at all, right? In that case, you will not be able to train. So we always prefer a model with a less number of parameter, right? And the other problem is the burden that you are giving, you are putting on the gradient descent algorithm. The gradient descent algorithm has to come up with optimal values for all these parameters. So you have to wait for a long time to get the optimal values for all these parameters. And the other important issue is scalability. So because of these reasons, you cannot scale an artificial neural network, right? So if you're not able to scale, then again, you will not be able to come up with a better model. See, I have a model with a 2-layer, and there is a chance that if I increase the number of layers, then I may get a better model. But I cannot increase the number of layers because if I increase the layer, then the number. So when we design a neural network, we have to make sure that the model is learning, right? So assume that we have to do some kind of classification or segmentation, and we developed a model, and we have to make sure that the model is learning, right? So since developing a model is again a trial and error approach, we always start with a simple model. So we assume that we developed a neural network. And we have some input. We will give the input to the model, and we have to see what is the predicted output. If the predicted output is not close to the expected output, then we will update the parameters of the model, and we will continue this process, right? And just assume that see, your error is not coming down. If your error is not coming down, that means your model is not learning the training data, right? If your model is not learning the training data, that means your model is too simple. Your model is too simple to learn the input data, and what you have to do is you have to increase the complexity of the model. So whenever we design a model, the generalizability of the model is very important. So your model should not overfit, and your model should not underfit. So to train the model or to develop a model, usually we will be having the train data, validation data, and the test data, right? So we use the train data and the validation data to develop the model, and to test the performance of the model, we use the test data. So the difference between the test data and the validation data is that the test data is unseen data. So the validation data we use to fix the hyperparameter. Both the train data and the validation data, the model will see when we develop the model. But the test data is unseen data. So now how we will check whether our model is learning the training data. So we will be having the input data, and we will give the train data to the model, and then you have to observe the train loss. If the training loss is coming down, that means your model is learning the training data. So that is a good symptom, right? We should also look at the validation loss. So if both the training loss and validation loss is coming down, then it is good. Our model is generalizing. So assume that the train loss is coming down, and the validation loss is coming down, and after some time, if the validation loss starts increasing, that means your model is overfitting. So make sure that the model is not overfitting and the model is not underfitting. Underfitting means the model is not learning. Your model is not learning the train data. Overfitting means your model is learning everything from the training data. Maybe if your data has some kind of a noise, your model will learn that noise also. So this is demonstrated with these figures. So you just assume that so this is what the model has to learn. So we have some samples. This is a true function. This green line is the true function, and we are going to generate some samples from this green line. These blue dots are the samples generated from the green line, and you can see that these blue dots are not exactly on the green line. That is because there is some noise. So this is a sample I generated, sample plus some noise. That is why these blue dots are not exactly on the green line. So these are the samples that I generated, and here I tried to come up with a function that fit this green line, and so I use a polynomial of degree 1, and this is the prediction. So since I use a very simple model, we can see this is underfitting, right? So degree with the degree 1, this is not underfitting, this is not fitting the so you can see that see here I use a polynomial of degree 1. Since I use a polynomial of degree 1, so this is not fitting properly. That means my model is underfitting, and this is because my model is too simple. So what I did is I increased the complexity of my model. Now I think there is some noise coming. Yeah. So what I did is I increased the complexity. So here I use a polynomial of degree 1. From degree 1, I am going for a polynomial of degree 4. So you can see that now it's fit better. So this is the model, that blue line. It is almost fitting the green line. So what I did is I again increased the complexity. So I use, instead of, when I found that this is fitting properly, I increase the complexity again. So you can see that here I use a degree of polynomial, a polynomial of degree 15, and you can see that this is fitting the blue dots perfectly. So this is not what we want. So we want a model that fits the green line, but here we end up with a model that is fitting this blue line very perfectly, right? So that means the model not only learned this green line, it is also learning the unnecessary noise in the data. So we don't want a model that learned the noise. So you should be very careful when you design a model. Make sure that the model is not underfitting and the model is not overfitting. So you can look at the training loss and the validation loss to see whether your model is underfitting and underfitting or overfitting. So if your model is underfitting, increase the complexity of the model, then your model will start learning. If your model is overfitting, then you can reduce the complexity. So you can use some kind of regularization technique to reduce the complexity of the model. So this should be less. So the test error minus train error value should be very less. And you can see that this depends on the capacity of your model H and the number of training samples. If your training samples is very less, and if you are using a model of very high capacity, then there is a very high chance that your model will overfit. So in that case, either you should reduce the capacity of the model, you should use a small network or a simple network, or you should increase the number of samples. So the capacity of your model, again you have to design a model with a different capacity. That you should also look at the training samples that you have. So if you design a very complex network with so many layers, and if your training samples are very less, then there is a very high chance that your model will overfit. And other thing that I want to discuss is the different ways you can try this gradient descent. So gradient descent we already discussed. So we use gradient descent to update the parameters of our model, right? So you can use gradient descent in different ways. So usually assume that you have n samples. So if you have n samples, so first we will give one sample, and you can compute the derivatives. Then you can give the next sample, you can compute the derivative. You can give third sample, you can compute the derivative, and you can continue this process till you finished all these n sample. Then we will take the mean of all those values, right? This is called the batch gradient descent. That means you use all the samples to do this weight updation. So this is how we update the weight. So W nu is equal to W old minus alpha into this value. So when you have n samples, you have to compute this derivative with respect to all the samples. So that means all the samples should be in the memory, and this process will also take time. So the drawback with the batch gradient descent is you have to load all the samples in the memory. So if you have millions of samples, then you have to load all those samples to the memory to do one weight updation. So this is one problem with the batch gradient descent. And you know that especially when you work with neural networks, you need a large number of samples to train the model. And if you are using batch gradient descent, then if our model is very heavy, and if you want to use a batch gradient descent, then we have to load our model as well as all these samples to the memory. So sometimes our memory will not be able to accommodate the model and this many number of samples. So you will not be able to use batch gradient descent. So the solution is you can use a stochastic gradient descent. In the stochastic gradient descent, you can update the weight on the run. That means with just one sample, you can update the weight. So assume this is the new value and this is the old value. So you can give one sample and you can update the weight, and you can give the second sample and you can update the weight. So the advantage in the case of stochastic gradient descent is so you don't need to load all the samples to the memory to do the weight update. So you can do the weight update with just one sample. But however, the problem is the weight update will not be accurate. So your estimation will be a biased estimation, and as a result, this will take more time than a batch gradient descent to converge. But batch gradient descent will converge better than stochastic gradient descent, because the estimates of the when you do the estimate of the derivative, it will be less biased when compared to the stochastic gradient descent. So as a compromise, what you can do is, instead of batch gradient descent and stochastic gradient descent, you can go for mini batch gradient descent. So if you have 100 samples, you can divide these 100 samples, say for example, into 10 batches, each batch of size 10, and using this small batches, you can update the weight. So this is a compromise between batch gradient descent and stochastic gradient descent. So usually whenever we use gradient descent, it will be batch gradient descent, right? So if you look at different papers, you can see they may mention that we use a batch size of 4, 8, etc. Right? If a batch size of 4 means they used say each batch consists of 4 samples, right? So this is a compromise between batch gradient descent and stochastic gradient descent. So here you can see the performance of different gradient descent algorithms. So in the case of, if you look at the trajectory of these three methods, you can see that the batch gradient descent converge. So if you look at the trajectory, you can see a smooth trajectory from this point to the local minima. So it converges better. Here you can see that the estimations are noisy, so it will take more time to reach the global minima. So, and if you look at the mini batch gradient descent, you can see that even though the performance of mini batch gradient descent is not as good as batch gradient descent in terms of this trajectory, but still it is better than the stochastic gradient descent. But however, if you want to use batch gradient descent, then as I told, the memory requirement will be more when compared to stochastic gradient descent. So you need a large amount of you need a GPU with a big memory if you want to use a batch gradient descent, and usually that will be more costly when compared to a stochastic gradient descent, right? Okay, so I think I gave an overview of how this artificial neural network work. So if you have any questions, you can ask me. Thank you.